Hello everyone, welcome to Augment Tech. We empower engineers for better career opportunities. Today, in this session, we will learn about ultrasonic testing. So, let's start. After the end of this tutorial, you would be able to understand ultrasonic testing, understand its working, understand what is a wave. You will understand different types of ultrasonic waves, understand applications of UT, its advantages, and limitations of UT. Okay, so let's start with ultrasonic testing. Ultrasonic testing is the transmission of high frequency sound waves into a material to detect imperfections or to locate changes in the material properties. In ultrasonic testing, high frequency sound waves are sent into the object. The sound waves travel through the material and the waves are reflected at the interfaces. The probe picks up the reflected wave and an analysis of the signal is done. Ultrasonic examinations can be conducted on a wide variety of material forms, including casting, forging, welding, and composites. As mentioned, it uses short pulse waves with frequencies ranging from 0.5 to 25 MHz, and sometimes frequencies up to 50 MHz are also used. Because this method has higher power potential than other entity techniques, ultrasonic testing can produce images that are more clearly defined than other methods and indicate characteristics deeper than surface level. These high frequency sound waves are transmitted into the material to characterize it or for flaw detecting. A considerable amount of information about the part being inspected can be collected, such as the presence of discontinuities, part or coating thicknesses, and acoustical properties. Now you must be wondering that why is it used? As an entity method, it is very ideal for detecting flaws and defects without damaging the object or material being tested. Periodic ultrasonic inspections can also be used to check for corrosion or for the growth of known flaws, and thus potentially prevent to a failure of a part, component, or entire asset. It is used in a wide range of industries, including aerospace, automotive, construction, medical, metallurgical, and manufacturing. Now, let's understand how does it works. The basic principle of UT of material is the propagation and reflection of sound wave. As an example, a test piece is shown in the animation. The longitudinal section through the test piece shows the position of the atoms extremely magnified and simplified as a single crystal. To begin with, a rigid, unyielding stop is attached to the right front end of the test piece, and at the left front end, a disc is installed. It will be used to transmit and receive sound waves. So, if a sound wave is generated at one end of the workpiece, it will travel through the material with the speed of sound. At the free end of the workpiece, the sound wave is reflected and it returns to the transmitter, which then acts as a receiver. Pushing and pulling at the disc causes a longitudinal sound wave to propagate through the cylinder. When the sound wave reaches the rigid stop at the right side, it is reflected and runs back towards the disc, which is now serves as a receiver. For UT of a test piece, not a very large transmitter is used in most cases, but rather a compact one which generates a short ultrasonic pulse is used. You can see in this diagram that at a place free from defect, the UT pulse travels to the right pulse end, which is also known as back wall. The pulse is reflected and recorded again as an echo. Now, when the transmitter is moved little downward, the cavity reflects a part of the wave. You can see here that the part arrives earlier at the transmitter than the rest of the sound wave. Even further downwards, the cavity reflects the complete ultrasonic pulse, as seen here. For material testing, either the echo of the defect can be utilized. This is known as pulse echo mode, or the phenomena that hardly any sound wave pass through the imperfection. This is called through transmission mode. In the given slide, a cylindrical test object is shown. It is having a defect inside it. Above that cylindrical test object, there is a UT test probe placed on it. In a pulse echo mode, a transducer is installed in a probe which performs both sending and receiving of the ultrasonic pulse. On a computer monitor, the strength or amplitude is being plotted upwards on the y-axis, whereas the time is plotted towards the right on the x-axis. In the given animation, you can see that with a probe at a place free from defect, only two signals may be seen on the monitor: the transmission pulse and the echo resulting from the lower surface of the workpiece. It is also known as back wall echo. Moving the probe towards the right leads to an additional echo created by the defect. You can see in the graph that the first echo is due to the transmission, the last one is the back wall echo, but here we are getting a new echo in the middle. It is due to the defect, and it is this echo which we have to study in pulse echo mode. Now, if we move further towards the right and send the transmission pulse into the test piece, now let's observe what will happen. Here in the graph, only the defect echo is visible apart from the transmission echo. There is no back wall echo in this graph. It is because whole of the transmission pulse is being reflected back by the defect itself. Now we are ready to understand the principles of ultrasonic inspection. First, we will get a general idea about a basic ultrasonic process. Ultrasonic inspection uses a piezoelectric transducer connected to a flow detector, which in its most basic form is a pulsar receiver and a oscilloscope display. The transducer is passed over the object being inspected, which is typically coupled to the test object by a gel, oil, or water. This couplant is required to efficiently transmit the sound energy from the transducer into the part. So, the first step is introduction of ultrasonic waves. Ultrasonic waves are introduced into a material where they travel in a straight line at a constant speed until they encounter a surface. Second step is reflection and transmission of wave energy. At surface interfaces, some of the wave energy is reflected and some is transmitted. Moving on, third one is calculation or information analysis. Now, the amount of reflected or transmitted energy can be detected, and it provides information about the size of the reflector, that is a flaw. Also, the travel time of the sound can be measured, and this provides information on the distance that the sound has traveled. Now, let's understand a wave. To understand what is ultrasonic energy and how ultrasonic energy propagate in a medium, let's take one example. The example of the vibration of a weight attached to a spring. As seen here, a weight is attached to a spring. At its equilibrium position A, two forces are acting on it. One is gravity force G and another is spring tension T. When weight is moved from position A to B, the tension T increases. If it is now released at position B, weight would accelerate towards position A under the influence of this increase in tension. At position A, the gravity G and tension T will again be equal, but as now weight is moving with certain velocity, it will overshoot A and it will move towards a position C. At this position C, the tension T decreases, so weight will fall towards A again. As the weight is moving with a certain velocity, it will overshoot A again and move towards B. As the weight moves between A to B, B to A to C and C to A, and the whole thing repeats again and again. This movement of weight can be plotted on a graph as shown here. Now, the sequence of displacement of weight from position A to B, B to A to C and C to A is termed as cycle. The number of cycles per second is defined as the frequency of vibration. The international term for a cycle per second is named hertz, and 1 cycle per second is known as 1 hertz. Now, the time taken to complete one cycle is known as the time period of the vibration, and it is represented by T. Time period is inversely proportional of frequency. The maximum displacement of weight from A to B or A to C is called the amplitude of vibration. As seen here, during the time period of vibration T, a wave travels a certain distance in the medium. This distance is defined as the wavelength of the wave and is denoted by the Greek letter lambda. The speed with which the energy is transported between 2 points in a medium by the motion of wave is known as the velocity of the wave. As we know that the speed is equal to distance upon time. Here, the distance traveled by wave is its wavelength and the time taken by it to complete one cycle is its time period. So, speed of the wave is equal to lambda upon time period. Velocity depends on the density of the material, and in the same material, it is independent of the frequency of the waves and the material dimensions. Let's discuss about different type of ultrasonic waves. First one is longitudinal or compressional wave. In this type of wave, the particle vibration and the direction of wave propagation is parallel. Alternate compression and rarefaction zones are produced by the vibration of the particles. Some of the properties of this type of wave is that the velocity of longitudinal wave is maximum as compared to other type of waves. Also, it is able to propagate in solid, liquid and gas. Moreover, it is easy to generate and detect. Generally, the TR probe and normal probe transmit longitudinal wave into the material. We will learn about these type of probes later in this unit. Another type of wave is transverse or shear ultrasonic wave. The direction of particle displacement is at right angles or transverse to the direction of wave propagation. The velocity of shear wave is 50% as compared to the velocity of longitudinal wave. Also, they can only propagate in solid only. In ultrasonic inspection, angle beam probe transmits transfer waves into a material. Moving further, third type of wave is surface or Rayleigh waves. The surface wave travel along the flat or curved surface of thick solids without influencing the bulk of medium below the surface. The depth to which these waves propagate below the surface with intensity is approximately equal to wavelength of the wave. Practically, all of its energy is attenuated within this depth. These waves are used to detect crack or flaws on or near the surface of test object. During the propagation of surface wave, the particles of medium describe elliptical orbits. Some of its properties are its velocity is almost 90% of the transverse wave. It can propagate in solid only. These types of wave are transmitted by the surface wave probe into the material. Also, one thing is to notice that they can only propagate in a region no thicker than about one wavelength beneath the surface of the material. Okay, moving on. The fourth type of wave is lamp or plate wave. The lamp waves are produced in thin metal whose thickness is comparable to the wavelength of ultrasonic wave. If a surface wave is introduced into a metal that has a thickness equal to or less than the wavelength, then a plate wave will result. The velocities of these waves depend not only on the type of material but also on the material thickness, the frequency, and the type of wave. The particle vibration in these type of wave are of two types: symmetrical or dilational and asymmetrical or bending. In the first one, the longitudinal particle displacement takes place, while in the second, transverse particle displacement takes place. These type of waves can propagate only in solid, and a special type of ultrasonic probe known as plate wave probe transmit is used to transmit these waves into a material. Now, let's have a look at some of the applications of UT. Flaw detection. It is mostly used for flaw detection such as cracks, inclusion, porosity, etc. It is one of the most widely used method of inspecting weld. Full penetration groove weld is possible by angle beam shear wave examination. Erosion and corrosion thickness gauging. Ultrasonic thickness gauging is routinely utilized in the petrochemical and utility industries to determine various degrees of corrosion and erosion. Thickness gauging applications include piping systems, storage, and containment facilities such as pressure vessels. Assessment of bond integrity. It is also used for the assessment of the bond integrity in adhesively joined and braced components. Another application of UT is the estimation of void content in composites and plastics. It is also used for the measurement of case hardening depths in steels. We can use ultrasonic to determine hardness depth of shafts, rods, tubes, and other cylindrical parts. Now we will look at some of the advantages of UT. Minimal part preparation required. In UT, we don't have to prepare the part as extensively as we have to in other methods. Sensitive to both surface and subsurface discontinuities. Thick specimen takes no more time to examine than the thin ones. It is sensitive to both thicker and thinner material for detecting surface and subsurface discontinuities. Depth of penetration for flaw detection or measurement is superior to other methods. It has high accuracy in determining reflector position and estimating the size and shape of the flaw. Access to only one side of component is needed. Only single-sided access is needed when pulse echo technique is used. Electronic equipment in UT provides instantaneous results. Moreover, detailed images can be produced with these automated systems. We can say that in UT there is no radiation hazard as there is with radiography, so it is safe as comparable to radiographic technique. Now we have reached the last topic of this unit: limitations of UT. Surface must be accessible to transmit ultrasound. Cast iron and other coarse grained materials are difficult to inspect by UT due to low sound transmission and high signal noise. Therefore, UT method can only be used on the surfaces that can transmit ultrasound. Skill and training is more extensive in this method than with some other methods. A high degree of operator skill and integrity is needed. Hence, the need for trained and certified entity personnel is very significant in this method. It normally requires a coupling medium to promote transfer of sound energy into test specimen. A UT technique cannot work without a good couplant. Therefore, this technique can only be used on those objects on which a couplant can be applied. One more limitation of UT is that linear defects that are oriented parallel to the sound beam may go undetected. Also, materials that are rough, irregular in shape, very small, exceptionally thin, or homogeneous are very difficult to inspect by this method. Moving on, reference standards are required for both equipment calibration and characterization of flaws. A UT cannot give us accurate result until and unless reference standards and proper calibration is used. Therefore, without the proper calibration, false results can be obtained. Alright, that was all about ultrasonic testing, its working, about wave, types of ultrasonic waves, applications of UT, its advantages, and its limitation. Hope you enjoyed the session. See you again in the next one.